Good afternoon. Thank you for being here. And this talk can actually almost be viewed as a sequel to what we just listened to, and also that talk draws nicely onto the talk in the morning about the multi-factor investing portfolio optimization. So it will be about multiple criteria risk contribution optimization, and the road that we are going down in the following next 20 minutes will be about an overview for those who are not really familiar with the concept of risk budgeting or risk parity optimization. Then the problem formulation itself will be briefly introduced. The structure of the accompanying package called mcrp, which is available on GitHub, will be presented. And finally, I will also provide an empirical application, but just to point out some of the characteristics when one is doing this mcrp optimization. Finally, I conclude with a summary and also mention some caveats with this approach. But let's get started first. The concept of risk parity was actually introduced into the literature by Qiang now more than 10 years back. And what it's all about is basically to seek a portfolio allocation such that there's no risk clustering. That means that each of your assets in the portfolio have the same contribution to the overall portfolio risk. And when I speak about risk, I do refer to portfolio standard deviation risk. So that was back more than 12 years. Now recently, Beitinger, in an article or in the Journal of Portfolio Management, proposed extending this approach to the higher portfolio moment risk, that is to skewness and to kurtosis. So with other words, we are now seeking a portfolio allocation such that has no risk clustering or almost no risk clustering with respect to the portfolio standard deviation risk, but by the same token also minimizes risk clustering with respect to the higher moment portfolio risks, i.e. skewness and kurtosis. So how does this all work out? That's more or less, Greece, we could have shared slides. So here are the definitions of the portfolio standard deviation risk, i.e. variance, the second moment, and then in the middle and last line, you do see the formulas for the portfolio kurtosis and the portfolio skewness risk. And as one can see, these are, with the Kronecker product, these are really tensor products, and the dimension was already referred to in the last talk, so I will skip that here just to show you the definitions which are also provided in John Doe and Rocking in that paper. So what comes next is then in the portfolio optimization context, you would like to have basically the same marginal risk contribution. So when you do the computation with respect to the first derivatives to these second, third, and fourth moment, you end up with the left column formulas, and then the absolute risk contributions are defined in the column of the right. And such to reiterate, the dimension problem, these are all more or less centered tensor product matrices, and you can see by the indices, by the kind of indices as well as the dimension, that when one is tackling larger portfolio optimization problems, that there is of course a problem with the count of estimation. And as Dries nicely pointed out, there are means to economize on the computation of these product moment matrices. So here we have basically our equations, our formulas for computing the risk contributions of our portfolio constituents with respect to portfolio standard deviation risk, with respect to the portfolio skewness, and the portfolio kurtosis. So now how this fits all into our optimization problem is as follows. It's just a simple weighted sum approach. So we are taking the dispersion of our risk contributions with respect to portfolio standard deviation risk, with respect to the skewness, as well as the kurtosis, and we weight those. So the weighting is here by accomplished with these scalar values named lambda 1, lambda 2, lambda 3. And of course, then our portfolio optimization, viewed from the perspective of a long-only investor, is subject to a budget constraint and, of course, non-negativity constraints with respect to the weighting. So that's it. What's implicitly written here in that problem formulation is that you can also, dependent on your liking, you can also tweak a little bit these sub-optimization functions, i.e. you can either set a certain lambda value, say lambda 2 equal to 0, and then out of that optimization framework, the portfolio skewness completely drops out and you would optimize only with respect to the risk contributions with respect to the portfolio standard deviation risk and or the portfolio kurtosis. Likewise, when you think or when you somehow would like to have an emphasis on the portfolio skewness and would like to make sure that really the dispersion with respect to the portfolio contributions of your constituents with respect to the portfolio skewness risk is small, then you could say double up the value for lambda 2 and keep the other the same. Now, and this draws on last year's talk. What's really important when one defining are those portfolio risk contributions is that they are all in the same ballpark. So that means it's pretty important that one is casting here the risk contributions in terms of percentages and not as the sum of the actual value of the portfolio kurtosis, skewness, slash portfolio variance. So that's basically what it all takes. Weighted sum approach, you have your three ingredients, the dispersion of your risk contributions with respect to the portfolio standard deviation risk, your dispersion with respect to the portfolio skewness, as well as then finally the kurtosis. That brings us to the second major topic in that presentation, namely the structure of the MCRP package. It's purely written in R. It has dependencies to the test that package, that's just for unit testing. And as also implicitly mentioned in the previous talk, it just takes as simple as the LMNIB function for conducting this type of multivariate or multi-criteria optimization. The core function, of course, of this package is the same as the package name itself. And then we do need in total, 9 auxiliary functions, namely firstly to compute the portfolio risk in terms of standard deviation risk or variance risk, then likewise for the portfolio skewness, for the portfolio kurtosis. We do need functions for computing the derivatives with respect to those higher moments, as well as then the contributions. So these are those 9 functions that are called implicitly inside that major function, that core function, MCRP. Code is available on GitHub, so please check it out. And if you have suggestions for improvement, just drop me a line. So now so that was the broad structure of the package. Now looking a little bit under the hood. So how is that core function MCRP casted? Well, it just takes, of course, a starting vector with starting values. Then, of course, you need to provide returns. And here, in contrast to what Reese said, it's just the sample estimators that are computed under the hood. So no shrinkage, something like that. It's just as simple as the sample estimator for the higher moments. So returns is just your matrix of your asset returns. And then you have that lambda vector. And here, you are free to set those values. When you set one value to NA, one element of that vector to LA, then that part of the sub-objective of the objective function just drops out of the optimization. And when you would like to double up, you would then just place a 2, for instance, as second element. So here you have complete freedom to do the weighting of these 3 sub-objective functions. And the ellipsis argument, well, this is passed down to the optimizer, to the LMM IB optimizer. So what does this function spits out? Well, it spits out an argument of S4 class, port Sol, that is defined in the FRAPO package. And when one takes a look at that formal S4 class object, it does have a slot with respect to the weights. That's what we are after. Then it does obtain an element opt, which is just a list object, what is returned by the optimizer, and that comes in handy to checking your solution, whether there you have convergence issues, etc., etc. Then there's also a character slot, which gives you a brief description of what you've really accomplished. And finally, it also has a slot call, which is of class call, and that comes in handy when you're doing updating. So now comes the empirical application to see how that all works out. And what I used here is basically a simple multi-asset data set contained also in the package FRAPO. It's month-end data. Data source is Yahoo, and I think Joshua has now fixed that bug or whatever it was called, such that you can pour in again data from Yahoo. But this is a pretty old data set, so ending in November 2011, but feel free to update the data and play around with it. And so that's the data set I will use here in the empirical application. And as I said, it's just to give you some feeling and some impression how everything works out. So therefore, I decided the following setup. I conduct portfolio optimizations just only with respect to the standard deviation risk, the contributions to the portfolio standard deviation risk, then only with respect to the portfolio skewness for the kurtosis, and then I blend the higher moment optimizations together to really make it a multiple criteria optimization. So that is, one would run an optimization where one is seeking an allocation such that the contributions to the portfolio standard deviation risk and to the portfolio skewness risk are minimal. Likewise, with respect to risk and kurtosis, and then finally, all three of them. So this brings us first to the R code. So you just invoke the library mcrp. You load the dataset, multi-asset, and here I just extracted a subset consisting out of 5 assets, 4 equity, 1 gold. That makes it multi-asset in quotes. Just compute the returns from a numerical point of view. It pays if you work with returns as percentages and not as decimals. And in the table, just to give you some clue, I computed, so to speak, for the marginals, the risk, the standard deviation risk, the skewness, and the kurtosis of these return streams. And this is a pretty typical picture that one encounters when one is dealing with financial market returns, i.e., in particular when it's equity and commodity, you have negative skew and you have excess kurtosis. What I would like you to bear in mind is that all of these assets have a negative skew, and I will come to that later. And as one can see, there's some dispersion with respect to the levels of the standard deviation risk, as well as the skewness and the kurtosis. So next comes the code, which is just doing the optimization with respect to those 6 portfolios. So you call, in the second line from the top, you just call that core function mcrp. We initialize with an equal weight allocation. We have our return matrix, and then that lambda, as you can see, we just provided a 1 as first element and set the other 2 to NA, and that means this is basically a pure ERC, equal risk contribution or risk parity optimization with respect to the portfolio standard deviation risk. The argument lower equals 0, so that's part of that ellipsis argument that gets passed down to the optimizer. Hence, we avoid negative allocations. And in the following lines, we do the same optimizations now with respect solely to minimizing the dispersion of the risk contributions with respect to the portfolio skewness, and finally, as third, solely with respect to the portfolio kurtosis. And as you can see in the following three lines with respect to setting of the lambda vector, we treat then dispersions to the portfolio contributions for the portfolio standard deviation risk, likewise as bad as dispersion of the contributions to the portfolio skewness. So because both have a lambda value of 1, so they are treated both as the same bad. Finally, to also save a little bit here on space, we are just putting everything into a list of those port-Sol objects, and we could then easily check the solutions by just drawing the solution from the opt slot and let the convergence statistics print out. So all 0, all good. Let's take a look here at the weights. So when you somehow recall the portfolio standard, the standard deviation of the returns, the skewness for each of those 5 return series, as well as the kurtosis, you will see that those marginal higher moments of the return somehow show up here also in the allocation. Just to give you a clue, take a look here, for instance, at the take a look here in the first column, which is an ERC allocation. When you go back, you see that you see here that emerging market equity has the highest risk, namely roughly 8% in that instance. So when you go down, you see here in the pure ERC allocation, because it's so risky, it has, from an intuitive point of view, it will obtain the smallest weight such that the risk contributions do balance. And by the same token, or similar reasoning, the same can be, just from an intuitive point of view, can be said for the other portfolio optimizations. Also, what's kind of interesting is that with respect to the Standard & Poor's, as well as probably with respect, fair to say, for the German equity market, those stay pretty much the same. They do, the weights do not change across which type of higher moments you are factoring in. The opposite is true when one takes a look at the FTSE and gold and emerging market, because it's so risky, it always gets, regardless of what you, of how you cast your optimization problem, is always the least invested asset. So this is really not telling a lot, but what is quite interesting to look at what impact and what difference those higher portfolio moments can make is when you compute first the moments of these allocations with respect to portfolio risk, skewness, kurtosis, but then also, and that's here in that line where one calls the portfolio risk contribution, the portfolio skew contribution, and the portfolio kurtosis contribution, as an aggregate measure, I computed here the standard deviation of these risk contributions for the various for these various 6 optimizations that are run, and the result is here. So first is ERC, then comes a pure skewness optimization, a pure kurtosis optimization, then multiple criteria optimization with respect to risk and skewness, and then risk and kurtosis, and then finally the 3 of them. And the portfolio characteristics with respect to these 3 higher moments are provided in the top panel of that table, but the meat is when one takes a look at the standard deviation of the risk contributions in the lower panel. So for pure ERC optimization, of course, the standard deviation of your risk contributions with respect to portfolio risk is 0. But then what you can see, the standard deviation with respect to the skew contributions and the kurtosis contributions, they are quite markable. They are 0.12 and 0.10. And the overall average standard deviation, now viewing risk in terms of a combination of contributions with respect to the portfolio standard deviation risk, with respect to the contributions of to the skewness risk, as well as to the kurtosis, the average of all this is 700ths, roughly. So, how does that play when one is taking the higher moments into account, the risk contributions with respect to the higher moments? And here what we can see is the overall average standard deviation of the risk contributions can be halved when we take either the skewness alone, the kurtosis alone, or a combination of the higher moments into account. So in that sense, you can immunize your allocation with respect to these higher moment risks. And I'm now finishing up and coming back to the point made earlier, that basically this worked out real nicely because the solution is largely driven by the marginal, by the higher moments of your marginals. But think of it when you have really constituents that have a positive skewness and negative skewness. Ordinarily, you would be really after having the assets in your portfolio that are skewed to the right. But here, how that optimization is casted, you are running into trouble, in particular when you are a long-only investor. Or think of cases where you have highly right-skewed returns and fairly small negative skewed returns. Then what the optimizer will do, and this is really counterintuitive, it will penalize the asset which has a high right skew and will a lot into the assets that are slightly and more evenly balanced, maybe skewed slightly to the negative. So here one has to be just cautious, and it's highly recommended first to take really a look what the higher moments are for each of your instruments that you are plugging into the optimizer, and maybe this should give you some guidance. And I do not want to say that approach is completely fruitless. It gives you a bit more balanced solution, but there are some pitfalls, in particular when it comes to being a long-only investor. And with that, I would like to end my talk.